Hello, I'm Julian Stander and I'm a lecturer in mathematics and statistics at the University of Plymouth. One of my research interests is in modelling the COVID-19 pandemic. So what I've got here in the PDF display is 4 graphs, and I want us to concentrate first of all on the graph in the top left-hand panel. And what I've shown there is the total number of documented cases of COVID-19 in Plymouth. The axis here starts on the 1st of March and goes on to yesterday's date, which was in fact the 15th of August. So we can see that the total number of cases in Plymouth increases. Of course it has to, because it's a total number on each day. And it increases up to a value which is now around about 700 cases. So in fact, in Plymouth, we've really done quite well in a sense with controlling COVID, in that compared with other places of a similar population. So here I've put Wolverhampton, which seems to have a rather similar population. We're performing a lot better. So you can see for Wolverhampton, the increase has been much higher, and the total number of cases at present is higher. So let's try to work with these data mathematically. And let's introduce some notation. So I'm going to use the notation YT to be the total number of cases up to and including day T. So what I'm actually plotting on this axis in this first graph here with the crosses is the total number of cases up to a particular day. And as I've said before, this YT is always increasing. Now you'll see on this graph that I've added a smooth curve, this black curve here. And this curve is a mathematical function that I've been working with in collaboration with a person called Giovanni Sebastiani, who is a leading Italian COVID-19 scientist. And this black curve here is based on the function ft, which takes the form a over exp, 1 plus exp minus t. In this formula, a is a positive constant. So the model that I'm showing there is what mathematicians would call a generalization of this function. It's a more complicated version of the one that I've written up here. But in fact, everything that I say can be illustrated. Every feature of our model can be illustrated by looking at this function here. So this function is an example of a logistic function. So what my research has involved is modifying the logistic function to find models for the COVID-19 pandemic. So what I want to do is to have a think about how this function behaves for large values of t and for small values of t. So let's first of all go to another page so we've got space to work with. Let's write down our function again. And let's see what happens as t tends upwards to infinity. Well, obviously, when t tends upwards to infinity, we're going along the horizontal x-axis here. T is getting bigger. So as t tends up to infinity, then it's pretty clear that minus t is going to tend down to minus infinity. And when I take the exp of both sides, which I'm allowed to do, then the exp of t will tend down to the exp of minus infinity, which is 0. So the upshot of this is that ft tends upwards, because the exp of minus t is on the bottom of the fraction. So ft tends upwards to a over 1 plus 0, which is just equal to a. So what that argument has shown is that if we plot ft against t, then here's a value a, and we know that as t gets bigger, this function tends upwards to a. Sometimes we refer to a as a limit or asymptote. So the function tends up to a. And if we look at our plots there, we can see a is going to be around the 700 mark for Plymouth. Similarly, we can ask what's happening as t tends to minus infinity. So as t tends down to minus infinity, then minus t is going to tend up to infinity, and therefore the exp of minus t will tend up to the exp of infinity, which is itself infinity. Just think about how the exponential function behaves. So this is telling us that ft is tending downwards to a over 1 plus infinity, and that's effectively 0. So as t gets smaller and smaller, this function decreases to the value of 0. And so that seems sensible behavior for the number of documented cases at a particular time. Okay. So if we look back at our graph, as I said before, our function is tending up to the value of 700. Whereas if we look at Wolverhampton, our graph is still increasing. So it's difficult at this point to see exactly where that's going to tend up to, but it's certainly going to increase to a higher level than the Plymouth value. But of course, we shouldn't be complacent about this. We've effectively been lucky in Plymouth for various reasons, and we should always follow the guidelines and take all the necessary steps to reduce the chance of a second wave. Okay, so now we've got a bit of mathematics set up. Let's extend what we've been doing. So let's remind ourselves that we're using the notation yt to be the total number of cases on day t. So that's the definition of yt. But we might also be interested in the number of cases that have occurred on day t itself, not the total number of cases up to day t, but the number of new cases on day t. So I'm going to write that as new with the subscript t. And we could find that by taking yt and subtracting yt minus 1. This is known as a first difference. So as an example of that, if it is the case that it is here that y19 is 12, so on the 19th of March there were 12 documented cases, and then on the 20th of March there were 14, then the number of new cases on day 20 is found as y20 minus y19, which is 14 minus 12, which is 2. So there are 2 new cases on day 20, and that was obvious from the numbers that I presented there. So the number of new cases on day t can be found by taking yt and subtracting from it yt minus 1. Let's just examine that a bit further and write that as in the following way. So that's yt minus yt minus 1, no change there. I'm going to divide that by t minus 1. Now, why can I do that? Well, that can be done because t minus 1 is just t minus t plus 1, which is just 1. So what I'm effectively doing in that expression is I'm just dividing by 1, which of course doesn't affect its value. So this reminds us of the definition of a derivative. Now, how is the derivative of a function f at time t defined? Well, it's defined as a limit, and it's the limit of a ratio. And the ratio is, well, we look at the value of the function at time t plus h, so a bit later on, and we subtract the value of the function at time t, and we divide through by the gap. So the gap is going to be t plus h minus t. Now, if we think about what t minus h minus t is, it's just t plus h minus t, which is just h. So we're dividing through there by the difference in the time, which is just h. And then the definition of the derivative says we look at that as h tends to 0. So the expression that we're seeing here for the derivative is a very similar expression to we're seeing here for the number of new cases on each day. So the real message of what I'm saying there is if ft represents the number of the total number of cases up to day t, then the derivative f dash t of ft is going to represent the number of new cases on day t. So by taking our model for ft and differentiating it, we go from a model for the total number of cases up to day t to a model for the number of new cases on day t. So let's now actually do that. So here's ft. So we've seen before that that's 1 plus exp minus t. Remember, a is a positive constant. And now we're going to differentiate this. So the derivative of this, we could write that as d by dt a over 1 plus exp minus t. And then we could take out a, because the derivative is a linear operator. So we get a d by dt 1 over 1 plus exp of minus t. And then I would write that as d by dt of 1 plus exp minus t to the minus 1. And then I perform that differentiation by using the chain rule. So first of all, I bring down the power. There's the power coming down. I'd then reduce the power by 1. So that becomes minus 2. But then I have to multiply that by the derivative of the function that's inside the bracket. So I've got to multiply that by the derivative of what I'm writing there, 1 plus exp minus t. So I get a times minus 1 times 1 plus exp of minus t to the minus 2. Now, when I differentiate 1, I just get 0. When I differentiate e to the minus t, I get minus exp to the minus t. In effect, I'm applying the chain rule again and then multiplying by the derivative of the minus t. If I simplify all this, I get, well, let's see what happens. This minus sign here cancels out with that minus sign there. So I get a exp to the minus t, all divided by 1 plus exp to the minus t squared. Now, it's a feature, or a very nice feature, of the exponential function that exp of x is always greater than 0 for any real number x. So what I can see from this is I've got a, which is a positive constant, I've got something that's positive, and then something that's positive on the bottom that's squared. So my derivative is always going to be positive. And that's good because it's modeling the y's, the total number of documented cases, which is always increasing. So the derivative is sensible. And what I'm plotting there on the bottom graph here for Plymouth, and again on the other side for Wolverhampton, is f-t. And remember, this represents the number of new cases on day t. So what we can see for the Plymouth case is that the number of new cases reached a peak, and the peak was around the value of 54, which corresponds to the 23rd of April. The black line that I've put here in the graph, the thicker line, is the day of the first day of the national lockdown. And therefore, we can see the effect of the national lockdown. It took about 30 days after the lockdown for the peak to appear, and then after that, things start to get better. So the effects of the lockdown seem to kick in after about 30 days. So this is the end of what I wanted to say about my research on COVID-19 modelling. As mentioned before, the model that we actually use for this is a little more complicated than the model that I've presented there, but it's basically a modification, a generalization of that model. We have recently extended further to allow for a second wave, so to allow for something that goes up and then goes up further. And that's also been work that we've been discussing with my colleague Tom Heinzel. And we, of course, hope that we won't need to use our model. We hope there won't be a second wave. In Plymouth, we've had relatively few cases, and you can see how well the model that we are working with fits the data. It explains those data very well. And of course, we can differentiate quite easily this function, and the derivative, as it always does in mathematics, is very useful and has a specific meaning. And in this case, the specific meaning is the number of new cases in each day. So I hope you've enjoyed this brief presentation based on some of the research into mathematics that we do at the University of Plymouth. And I thank you very much indeed for your attention.